All right. So before we get started, just notice this announcement that the homework number 6 is now posted up on the Google Drive, and it's due a week from today. So this is homework related to the stuff about representing operators as matrices and doing quantum mechanics with this matrix approach. All right, so now let's resume what we were talking about on Tuesday, right? And so on Tuesday, we started talking about quantum mechanics in 3 dimensions, right? And so yeah, we talked about ideas like having a wave function that is a function psi of position and time, and that means a function of x, y, z, and t. Right, and then a lot of the stuff that we did in 1 dimension just has to be scaled up from 1 dimension to 3. So, for example, Schrodinger's equation that shows how a wave function changes in time, right? We have IH bar, then the partial derivative of psi with respect to the 1 variable time, that has to be equal to negative h bar squared over 2m, and then the sum of all the second derivatives. So the second derivative with respect to x plus the second derivative with respect to y plus the second derivative with respect to z, right? All of these second derivatives. And then this whole combination is the Laplacian of psi. And then for the potential energy term, plus the potential energy as a function of x, y, and z times psi of x, y, z, and time. Okay, so this is a natural generalization of Schrodinger's equation in 1 dimension, going up to 3 dimensions, working in Cartesian coordinates, that is to say, x, y, and z. Okay, so now I wanted to just show you an example of solving a problem like this. Okay, and so when we were working in 1 dimension, we started with a particle in a box, right? So that is a 1-dimensional box, a limited range of x from 0 to a. Right? So now a natural generalization would be a particle in a 3D box. Okay, so let's suppose we have this rectangular geometry, like a typical shipping box. Like that, okay? And so here, x goes from 0 up to a, and y goes from 0 to b, and z goes from 0 up to c. Okay? And the potential energy is something that confines the particle in the box. And so this is a potential energy, V of x, y, and z is 0 if x is between 0 and a, and y is between 0 and b, and z is between 0 and c, and infinity otherwise. Okay, so this potential for sure is going to keep a particle inside of that box. Now we want to solve it with the same kind of method that we used for the particle in the one-dimensional box. Okay, and so in particular, that means we have boundary conditions right at the walls of the box, right? And so that means that psi goes to 0 on the walls. But in the interior, we have the potential energy equals 0. All right, so in the interior, we can just solve the Schrodinger equation with the IH bar time derivative is minus H bar squared over 2m, and then the Laplacian, right, with no potential energy term. So it's this stuff, plus 0, because the potential energy is 0 in the interior. Okay, so you remember that when we had a problem like this in one dimension, we solved it using separation of variables, right? And so in one dimension, we said, oh, well, the psi of x and t, let's guess that it's a function of x times a function of time. Okay, so that worked all right in 1D. Let's try the same kind of thing in 3D. Okay, so let's say we have a psi of r and t. It should be a function of position times a function of time. But then, even more strongly, we'll do separation of variables here too. Right? That is, we'll assume that the function of position r is a function of x times a function of y times a function of z. Okay? And so we could write that then as some big X of little x times big Y of little y times big Z of little z times phi of t. Okay, so it's a multiple separation, right? Separating x and y and z and time. So this is our wave function. It's a function of x, y, z, and t. Okay, so now let's put that into Schrodinger's equation and see what we get. Okay, so for Schrodinger's equation, right, on the left side, we have IH bar d psi dt. Okay, so this now is going to be equal to IH bar times the partial derivative with respect to time of this whole product. Okay. Now, if we want to take the partial derivative of that with respect to time, the first three things don't depend on time. So they just factor out, okay? And we only have to differentiate this factor, the phi of t, with respect to time. Okay, so this gives us IH bar, IH bar times, big X times big Y times big Z. this is a function of little x, little y, little z. I'm going to leave out these little arguments just to save on writing. Okay, so that times the derivative, actually I'll write it even not with the partial derivative symbol, but with the regular derivative symbol. Derivative of phi with respect, with respect to time. Okay, so that's on the left side, right? On the right side of the equation, there's a minus h bar squared over 2m, and we have the second derivative, well, the second derivative of psi with respect to x, plus the second derivative of psi with respect to y, plus the second derivative of psi with respect to z. Okay, so here, this is going to be equal to negative h bar squared over 2m. Okay, so first we have a second derivative with respect to x. Okay, but in this product of functions, only one of them depends on x, right? That's the capital X, right? Everything else is a constant with respect to little x. Okay, so the second partial derivative of the product with respect to x is just the second derivative of the big X function times big Y times big Z times phi. Okay, so that's the first term. Now we can add on the second term. Okay, here it's the same story, but with y instead of with x. Okay, so the second derivative with respect to y is the big X times the second derivative of the big Y function, dy squared. Oops, I forgot a square there. Dy squared times big Z times phi. Okay, and now for the Z part, we say, well, only one factor depends on little z, that's the big Z. Okay, so it's the second derivative of the big Z function with respect to little z, and then times phi. Okay. Now, you remember what's the next step in the separation of variables trick, right? The next step is to divide through by this whole product, okay? So let's do that, okay? So if I divide through, pick another color. If I divide through every term by big X times big Y times big Z times big phi. Okay, so I'll do that in every term. All right, so now in each place, most of the factors will cancel, right? And so here, XYZ cancels XYZ. Okay, here YZ phi cancels YZ phi. Here X Z phi Z phi. XY phi phi. Okay, so now we can simplify what's left. All right, so what's left is this I h bar, all right, the first term has a 1 over phi d phi dt. Okay. The next, on the other side, there's this minus h bar squared over 2m, and then the first term has a 1 over big X times the second derivative of big X with respect to little x. Okay. Then there's a term that's like a 1 over big Y, second derivative of big Y with respect to little y. And then 1 over big Z, second derivative of big Z with respect to little z. Okay, so now maybe you can remember what was the story that I told after this step in separation of variables, right? When I was doing this in one dimension, I said, okay, well, what does each of these terms depend on, right? It looks like the first term depends on only time and nothing else. This depends on, well, I'll say it depends on nothing but time, right? It does not depend on X, Y, or Z. Right? This term depends on nothing but X, right? It does not depend on Y, Z, or time. This term depends on nothing but Y, right? It does not depend on X, Z, or time. This term depends on nothing but Z, right? It doesn't depend on X, Y, or time. So how is that possible, right? How can something that doesn't depend on, X, Y, Z equal something that doesn't depend on Y, Z, and time, et cetera, right? The only way that that can possibly be true is if each of the terms here is a constant, which doesn't depend on any of these things, right? So we could say all terms must be constants. That is independent of X and Y and Z and time. So let's make up nice names for all these constants. And they can be names that are sort of analogous to what we expect from the one-dimensional solution we already did. Okay, so over here, we know what this thing is in the one-dimensional solution, right? In the one-dimensional solution, this is energy, right? And so we could say, let's call this constant E for energy. I bet it'll be energy again. Okay. And then let's make up names for these constants also. Right? In the one-dimensional problem, this constant, the X thing, that was a negative K squared, right? Where the solution was a sine KX. So let's call this thing negative K sub X squared. And this thing we'll call negative K sub Y squared. And this thing we'll call negative K sub Z squared. And then we must have a certain relationship among the constants. We must have that the E is equal to negative H bar squared over 2m, negative KX squared, negative K minus KY squared minus KZ squared. All right, and all these negative signs cancel. So it's the sum of those K squareds. Okay, so that means that in order for the separation of variables to work, we must have this relationship between our constants, right? The E and the 3 Ks. Okay, that's fine. So let's keep that constraint in mind. And now we have 4 separate differential equations to solve. Right? We have a differential equation in time, we have a differential equation in x, in y, and in z. Okay. So let's do it. Okay. So for the time equation, that's just like what we did before in one dimension. Okay, so for the time equation, we have I h bar 1 over phi d time is equal to e. Okay, so that means that d phi d time is equal to e phi over I h bar. So negative I e over h bar times phi. Right? So the first derivative is a constant times the function itself. Okay? You know how to solve this because we've been doing it all semester, right? This is that phi has to be this complex exponential of minus I e time over h bar. So this is just like one dimension. How about the x equation? Okay, so for the x equation, we have 1 over big X, which is the second derivative of big X with respect to little x, is equal to negative kx squared. Okay, so in other words, the second derivative of big X with respect to little x is negative kx squared times big X. So this looks just like the particle in a one-dimensional box. Right, and so we basically know the answer. Right, and so we know that there has to be a solution of the form, big X is capital A, say sub X, sine K sub X, plus B sub X, cosine K sub X. And this is a solution of the differential equation, but we need to also impose the boundary conditions. Okay, so there's a boundary condition at x equals 0 that the function has to be 0. And there's a boundary condition at x is a that the function has to be 0. So the first boundary condition, let's see, if we plug in little x equals 0, that tells us that a sub x times 0 plus b sub x times 1 has to be equal to 0. Okay, so the b term is 0. We only have the a term. And then the boundary condition at x equals a tells us that a sub x sine k sub x a is equal to 0. So that means either a sub x equals 0 or sine k sub x a equals 0. But if a sub x equals 0 and b sub x equals 0 also, then our function is just 0. Well, that's kind of a trivial solution. It's a non-solution. It's saying there's wave function 0 everywhere. Non-solution. So the only non-trivial solution is if sine of k sub x times a equals 0. So that is possible if k sub x times a is an integer multiple of pi. Let's call it n sub x times pi, where n sub x is some integer. So k sub x is n sub x pi over a. All right, and then our solution for this big X function is big X as a function of little x is some coefficient times sine n sub x pi little x over a. Okay, so that is the solution for the big X of little x function. Okay. Now, we need to do exactly the same thing for y and for z. I don't really have to go through all the steps because it's just the same thing, right? We're doing all the same steps again. Okay, so I'll just say similarly, we know the solution for big Y of little y. That should be some a sub y times the sine of n sub y pi y over b, because b is the system size in the y direction. So in other words, the k sub y is ny pi over b. And the same thing has to work for the z function. Okay, that it's some a sub z sine n sub z pi z over c, because that's the system size in the z direction. So the constant k sub z is n sub z pi over c. Okay, so let's now put the pieces together. And we will get a solution psi of x, y, z, and t. Okay? So that is going to be a product of ax times ay times az times 3 sines. The sine of nx pi x over a times the sine of ny pi y over b times the sine of nz pi z over c. And then all of this is multiplied by the complex exponential minus I e t over h bar. And here we have 3 constants multiplied together. There's no need to keep them separate anymore. Let's just call that A by itself. Okay, so this now is a solution of Schrodinger's equation in the box. Right? And so it satisfies Schrodinger's equation and it satisfies the boundary conditions on the box. And this works provided that we have the right relationship between E and Kx, Ky, Kz. Okay, so now that means E has to be h bar squared over 2m times nx squared pi squared over a squared plus y squared pi squared over b squared plus z squared pi squared over c squared. Okay, so this, this is a solution, right? And so we have found what I have been calling a special solution or a separable solution. Or in chapter 3, we learned to call it an energy eigenstate. And the corresponding energy, this E, is an energy eigenvalue. Now, you'll notice that there are a lot of these solutions, right? There's a lot because we said nx has to be an integer, and ny has to be an integer, and nz has to be an integer, but each of them could be any integer, right? So this is not, a single solution. This is, we found now a whole family of solutions, right? And so the solution is characterized by 3 integers. That are nx, ny, and nz. So maybe these things should go as subscripts, right? We could say, if we wanted to write a really detailed notation, this is psi sub nx, ny, nz. And this is E sub nx, ny, nz. Okay? So the same way that in one dimension, we had a whole set of solutions, right? There's a psi 1, psi 2, psi 3, psi 4, right, etc. Okay, here there's a psi sub 1, 0, or a psi sub 1, 2, 3, right? Or a psi 17, 11, 36, right? Any 3 integers give us a solution, and each of those solutions corresponds to an energy, E sub 11, 17, 11, 36, or whatever I said. Okay, so now we need then to put them together to make a general solution. Okay, so the general solution is a linear combination. So we could say that psi general as a function of x, y, z, and time is the sum over special solutions. Okay? So that means a sum over nx, and a sum over ny, and a sum over nz of some coefficient c sub nx, ny, nz, times special solution psi sub nx, ny, and z, which are functions of x, y, z, and time. All right, and so any linear combination like this satisfies Schrodinger's equation, just as we've seen in all the one-dimensional problems we've dealt with. And any linear combination like this satisfies the boundary conditions. So you ask, how do you know what these C coefficients are? And maybe you can guess the answer, that these things are determined by the initial conditions. Okay, so, if we know the initial condition, then we could plug in t equals 0 here and t equals 0 there. Okay, and then we know what's on this side, and we want to express it as a sum of coefficients times these special functions. The sine of something times x plus sine of some times sine of something times y times sine of something times z. And so then it's a three-dimensional Fourier series. All right, so a Fourier series in all three coordinates. And you can solve it with the same kind of method that we've done before in one dimension of taking the inner product with each of these sides. Right? You take the inner product of both sides of the equation, and that gives equations to determine each of those C's separately. I don't really want to do an example of that just now because that's kind of a messy thing to do. I want to show you something else that's maybe a little bit more unique to three dimensions instead of one dimension. Okay, so let's consider now a special case. And let's say the special case of a cubical box. So all three sides of the box are equal to each other. Something, this is supposed to be a cube. Okay, that's supposed to be a cube. So that means that A equals B equals C. In that case, our energy simplifies a lot, right? So our energy was this equation over here, all right? But now I'm going to plug in that A and B and C are all the same. Right? And so then we can say the energy is the h bar squared over 2m, and I'll factor out the pi squared, and I'll factor out the length squared. I'll call it a squared. Right? And then in parentheses, we just have an x squared plus an y squared plus an z squared. Okay, so this is the energy sub nx, ny, and z. Okay, now the interesting thing to notice is that there is a degeneracy. whoops, D, I forgot some letters here. Let me try that one again. Ha, 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 ha. Degeneracy of energy. So degeneracy means that different states have the same energy, have exactly the same energy. Okay, so let's find some examples of that. Okay, so let's think about the energy for state 1, 0, 0. Okay, so here I'm going to make up a notation where I have 3 numbers in the subscript. Oops. Where I have 3 numbers in the subscript. Okay, 1, 0, 0. Okay, so this is not 100. This is 1, 0, 0. I'm just leaving out the commas. And so that means nx equals 1, and y equals 0, and z equals 0. Okay, that's what E sub 1, 0, 0 means. Okay, and so this is equal to h bar squared pi squared over 2ma squared times 1 squared plus 0 squared plus 0 squared. Okay, so that's just h bar squared pi squared over 2ma squared. Okay, but you know, if I had E sub 0, 1, 0, that means and x is 0, and y is 1, and z is 0. Right? That energy is h bar squared over 2ma squared, 0 squared plus 1 squared plus 0 squared. Okay, so that's the same thing. And of course, E sub 0, 0, 1 is also the same. Okay, so we would say these 3 things are degenerate. Right? And there are lots of things, lots of sets of states you can make up that have degenerate energies in the same way. So just to pick another example, E sub 1, 1, 0 equals E sub 1, 0, 1 equals E sub 0, 1, 1. Okay, so these are 3 states that all have the energy of h bar squared pi squared over 2ma squared times 2, right? 1 squared plus 1 squared plus 0 squared. Okay, but by comparison, E sub 1, 1, 1, that's not degenerate with anything, right? That's has a unique energy all by itself, right? Which is h bar squared pi squared over 2ma squared times 3. Okay, and so this is not degenerate. All right, so this is an interesting physical point, right? Whenever you have a symmetry in physics, right, that different things come out to be the same, that's often leads to some remarkable physical behavior, okay? And here, the significance is that, you know, we already dealt with combinations of states when we were in 1 dimension, right? And what we found then was that if you have a single state, so I'll say in 1D, if you have a single state, there is no time dependence. But if you have a combination of states, there is time dependence. And that's like, you know, in my game of Pong, right? Where you have probability that's going back and forth from one side to another side of the box. Okay. In 3D, when you have the possibility of degeneracy, things get a little bit more complicated than that. Okay. We would say in 3D, if you have still, if there's a single state, there's no time dependence. But also, if you have a combination with degenerate energies, still there's no time dependence. And it's only if you have a combination with non-degenerate energies that you have time dependence. And the reason for that, what's the reason for that? The reason for that, well, suppose you have a combination with degenerate energies. Okay, so let's look for an example like this. Okay, so suppose that you have psi is x, y, z, and time is some 1/√2, and we have the state 1, 0, 0 of x, y, z times e to the minus energy 1, 0, 0 t over h bar. Okay. And plus 1/√2 psi 0, 1, 0 of x, y, z e to the minus I e 0, 1, 0 t over h bar. Okay. And now you want to make the probability density that goes with that. Okay. So the probability density, that is the absolute value of psi squared. Okay. So that means we want to take this wave function times its complex conjugate. So first we can, well, I'll write it out just to be clear. Okay, so that's this 1/√2 psi 1, 0, 0 e to the minus, well, psi star. So it's, yikes, what did I do? What did I do there? Okay, here's the complex conjugate. E to the minus I. It's lucky it came up the New York Times and not my photo collection or something here. But all right, so let's see. E to the plus I e 1, 0, 0 t over h bar plus 1/√2 psi 0, 1, 0 e to the plus I E 0, 1, 0 T over H bar. Okay, there's a complex conjugate, right? And then I'll multiply that times the original function. 1, 0, 0, e to the minus I E 1, 0, 0 T over H bar plus 1 over root 2 E whatever psi 0, 1, 0 e to the minus I E 0, 1, 0 T over H bar. Okay, let's multiply this stuff. Okay, so when we're multiplying the first thing times the first thing, you know that the time dependencies cancel, right? Because here you have positive complex exponential, a negative complex exponential, and they just cancel each other perfectly. Okay, so the first term in there, that is 1/2 psi 1, 0, 0 magnitude squared times e to the 0, right? There's no time dependence. Okay. Likewise, if you multiply the second thing times the second thing, the time dependencies cancel, right? So that makes a plus 1/2 psi 0, 1, 0 squared times e to the 0. Now we have the cross terms. Okay, so we have a cross term that is this thing times that thing. Okay, so let's think about what goes in the time dependence there. It is plus 1/2 psi 1, 0, 0 psi 0, 1, 0. There's an e to the I E 1, 0, 0 T over H bar times e to the minus I E 0, 1, 0 T over H bar. If these energies were different, that would give you some time dependence, right? But because these energies are exactly the same, the time dependence just cancels. And we get something independent of time. And likewise, we have psi, there's another term, the other cross term is 1, 0, 0, 0, 1, 0, minus I, 0, 0 T over H bar, e to the plus I, E 0, 1, 0 T over H bar. And those things also perfectly cancel to give you something independent of time, okay? So this is now another way to get a stationary state. We can have a stationary state, not just from one of our original separable solutions that we found. We could also get a stationary state by taking any linear combination of special solutions with the same energy. Any linear combination of separable solutions with the same energy. Okay. All right. So, this whole story, this is basically what I wanted to say about the particle in the 3D box. And probably the most important thing to remember here is that we have solutions that are analogous to the particle in the 1D box, but the solutions are characterized by the set of three numbers, nx, ny, and nz. Right? So it's a set of three integers instead of just one integer in one dimension. So one dimension, one integer, 3 dimensions, 3 integers. Right? And if you want to be fancy, you might call these things quantum numbers to describe what kind of quantum state we have for the system. Okay? And the energy depends on this set of quantum numbers. And the energy depends on that set in the way that we figured out, right? Sum of the squares of those things. Okay, so far, everything that I have shown you about 3 dimensions is kind of similar to 1 dimension, but just sort of scaled up a couple notches. And so this all works pretty well, okay? And so we might say, so what's not to like? Right? Maybe 3 dimensions really is like 1 dimension, but just bigger. And so the problem, okay, so the reason for wanting to do something that's more complicated is that in most physical situations, in most physical problems, the potential energy is not a simple function of x, y, and z. So if the potential energy were a simple function of x, y, and z, then you could say, all right, well, we've got Schrodinger's equation, and that's expressed in terms of x, y, and z. This second derivative with respect to x, and the same thing with respect to y, and the same thing with respect to z, plus v of x, y, and z times psi of x, y, z, and t. Okay. But normally, in most physical problems, this v of x, y, and z is not some simple function of x, y, and z. So in most physical problems, you can't do a separation of variables between x and y and z. You can still separate out time from x and y and z, but the whole business of saying it's a function of x times a function of y times a function of z, it just doesn't work because the potential energy depends on those things in some joint way that messes up the separation of variables. Okay, so I'll show you a typical example. In a typical example, we have what's called a central force problem. That is, V depends on the distance from the center. Okay. So you might say, for example, you have a proton at the origin. And you have an electron out here. And the proton is at r equals 0. And the electron is at some position r. And there's a potential energy for the electron. That is a Coulomb attraction to the proton. Okay? So the potential energy V of X, Y, and Z is some function of the distance from the center. And that means it's a function of the square root of X squared plus Y squared plus Z squared. So this is a problem that doesn't work in separation of variables between X and Y and Z, right? That if you try to do that, you don't get the nice kind of equation that you're looking for. Let me just show an example of that, okay? And so if we tried to put in that sort of thing, right, we would get I H bar, and here on the left, I'll say function of X times a function of Y times a function of Z times d phi dt, okay? And then on the right, we have H bar squared over 2m, and let's see, second derivative of the X function times Y Z phi plus the second derivative of the Y function times X Z phi plus the second derivative of the Z function, fine, okay, plus V of square root of X squared plus Y squared plus Z squared times X, Y, Z phi, okay? And now, if we try to divide through by X, Y, Z, and phi, let's see what happens. Oops. So if we divide through by X, Y, Z, and phi, then we would get to this situation where we have this thing, and that's go to this, 1 over X d2 plus 1 over Y d2 plus 1 over big Z d2 big Z Z squared plus, oh, we've got this V of square root of X squared plus Y squared plus Z squared. This V thing, this just kind of messes stuff up, right? It spoils our argument that everything has to be a constant. So, this procedure wouldn't work. Okay? I'll say it.
Dr. Sellinger,
Please.
Swastik just posted something in the chat if we're missing a negative term.
I'm sure we are. Here? Maybe there. Okay. Yes. Swastik, is that what you're looking for? I think so. So I made at least one mistake, but maybe I made more mistakes too. Yes. Okay, good. Thank you, Swastik. So the point is, this doesn't work in Cartesian coordinates. So it spoils our nice system for solving Schrodinger's equation, our nice system for solving this partial differential equation. Well, I mean, we could give up on separation of variables. We could say, I don't know how to solve this thing. I'll just type it into a computer and let a computer solve it. We could do that, I guess. But that would be a pity, wouldn't it, to give up on trying to solve things with pencil and paper. We'd be giving up on the kind of insight into the solutions that come from having some algebraic expressions. Okay, so there's an alternative, right? Instead of giving up on separation of variables, we could give up on Cartesian coordinates, right? We could say maybe there's some other coordinate system where the separation of variables will work. Okay? Maybe there's some other coordinate system that is naturally suited to the symmetry of the problem. Okay? And so in fact, that is the case. Okay, and so the point is, instead of using Cartesian coordinates, let's try using spherical coordinates instead. So, this is supposed to be a motivation to consider another coordinate system and work with another coordinate system, even if you already know and like Cartesian coordinates. Still, this is a problem where you can give up on Cartesian coordinates. So let's think about spherical coordinates, all right? So is this something, by the way, that you've covered in the math methods class? Yes, okay, good. So let me show you how and I think most American physicists would write these things, and you can tell me whether this is compatible with the notation that you got in that class. Okay. So, we have some three-dimensional Cartesian coordinates, x, y, and z, like that. And the idea in spherical coordinates is that you want to have a different way of describing any point. Okay, so in Cartesian coordinates, the point is described by x, y, and z. But now in spherical coordinates, let's think of a different way to represent where the point is located. Okay, let's think about where the point is located with respect to the origin, like that, and say, well, one thing that I care about a lot is what's the distance out from the origin. Okay? So the distance out is some distance little r. And so not a vector little r, but a scalar, a magnitude little r, the magnitude of the distance out. But then, that's not enough to describe a point, right? Because there are lots of points. Well, there's a whole sphere of points that are the same distance out from the origin. So we need to say, where on the sphere are you located? Okay. The standard way to do that is with two angles. Okay? So one angle is, what's the angle going down from the z-axis? So there's some angle from the z-axis to this straight line from the origin to the point in question. Okay, we call that angle theta. So theta is the polar angle down from the z-axis. So I can make that with my Apple Pencil, right? Going down. But then there's still a lot of points that are the same polar angle down. You also need to say where it is going around the z-axis. So to characterize that, we take this point and project it down into the xy plane. That makes a vector like this. And then we have another angle, phi. That's the angle with respect to the x-axis in the xy plane. And this is an angle called the azimuthal angle. Okay, and this is going around from the x-axis. Okay, so these two angles are related to latitude and longitude on the globe, right? So the phi angle, this is like longitude on the globe. It's saying, how far are you east or west from the prime meridian passing through Greenwich, England, right? And the polar angle, this is related to latitude. The slight difference is latitude is measured going up from the equator, right? And so how far north or south from the equator, but this is measured going down from the North Pole. So this is 90 degrees minus the latitude. So that means that in spherical coordinates, we have the three variables r, theta, and phi, which can describe any particular point. Okay. And so it's three different coordinates, right? Not the x, y, z coordinates, but three different coordinates. And so everything that we're accustomed to doing with x, y, and z, we can do with r, theta, and phi instead. In the next class, I will show you something about how to do calculus, how to do derivatives and integrals with those variables. But for now, suffice it to say, why this is a simple thing to do, a nice thing to do for these physics problems. And the reason is that that's typically what goes into the potential energy, right? That when we have a potential energy like this one, the potential energy is a messy function in Cartesian coordinates, but it's going to be a simple function in spherical coordinates because it only depends on one of the spherical coordinates, r, and it doesn't depend on the two angles. Okay? So the potential energy in any of these central force problems, the potential energy will be just V of r, independent of theta and phi, right? And so this is a huge simplification in the potential energy term. And so the other things that we do are going to get messier than in Cartesian coordinates, but it's worth it, right? It's worth having the extra messiness in everything else in order to get the simplification in the potential energy term. That will give us a way to solve a lot of these problems exactly. which I will get into doing on Monday. Okay. So I will stop for now. Please remember to take a look at that homework that I mentioned at the beginning of class. In any case, have a good weekend, and I'll see you guys on Monday.